Good afternoon, everyone. A very warm welcome to the very last session of the day. I'm here to give you the good news and the bad news about big data. Which do you want first? Do you want the bad news first or the good news first? I knew you were going to say that. I'll give you the good news first. The good news is there has never been a more exciting time to be in the big data or the analytics space. There is so much good stuff going on, so much is available to us to really drive some fantastic analysis. There's challenges, of course. The volume of data is growing, the variety of data is growing, the velocity of data is growing, all the 3 V's that we always hear about. But as the saying goes, necessity is the mother of invention, and there has been some incredible inventing going on in the last 5-10 years. You marry that invention with the power and the scale of the cloud, and you've got some fantastic technologies and tools to work with. That's the good news. The bad news is, how do you keep up? How do you possibly keep up with all the innovation? Whenever you wake up in the morning and you check your news, your feeds, wherever you get your info from, there's a new open source project that's been released, there's a new release from one of the vendors, Amazon's come out with a new service, Amazon's changed the service. How do you possibly keep up with that? And customers often say to me, you know, what's the best particular project or service for my use case? So the good news is this presentation will make it all crystal clear. In 1 hour, we'll have it all absolutely sorted. That's the good news. So what we're going to do as an agenda is we're going to look at an end-to-end framework for some of the big data technologies. I'm going to step you through how you might use the AWS cloud from end to end to start doing some analytics in an agile way. Once we've done that, we're going to layer on top of that some use cases, some common use cases that we see on top of those building blocks so you can kind of see how they're used in practice. And then at the end there, if the gods smile on us, we'll do a little demonstration as well. So that's our main agenda. I also want to sprinkle a couple of other items in there as well. I want to talk about the greater good that big data can do for us. I want to talk about religion. Yes, we're going to go there. And I want to talk about FOMO. I want to talk about the fear of missing out, and we'll cover that off as well. So let's first talk about the greater good. So when we look at big data technologies and all the analytics, great stuff that's out there, we always look at what that can do for us and look at what that can do for our organisations, and that's fantastic. But I think sometimes it's nice to take a step back and think about what can big data do for the greater good? What can it do for humanity as a whole? And there are a lot of men and women working in this field to really benefit all of us. And there's one particular project which is quite near and dear to my heart. I've had friends affected by this, and I'm sure you have as well. And it's the project that deals with people posting to social media when they've had too much to drink. It's a big problem. We've all done it. We've all been out late at night and we've pressed send on that text message that shouldn't have gone, or we've uploaded to Facebook a picture that maybe we shouldn't have. And there are different ways of dealing with this. So there's applications you can get on your phone which will hide your contact list from you, for example, for 5 or 6 hours. That kind of works to some extent. Or there's other apps that go a step further where they'll actually analyse your text message. If there's too many spelling mistakes, it won't send the message. If there's too much of a gap between the last word and when you hit send, won't send the message, assuming that you're fumbling for the send button. Thinks you're probably not in a fit state to send it. That's great, but I think the power of big data, if you look at what Facebook are doing now, they're actually looking at using some deep learning techniques to actually analyse your photos on the fly in real time to decide whether they think that's something you're going to be embarrassed about the next day. So this is the project that they've got going. They announced it last November. Deep learning techniques. So what they'll do is they'll actually train this machine learning algorithm on appropriate pictures and non-appropriate pictures. And then if it's inappropriate, then they won't send it for you. Thought that was a fantastic use of the technology that benefits all of us. That benefits the human race in a very meaningful way. That cow, by the way, is actually part of a different story. When I crop this, that's not actually supposed to be someone's embarrassing picture. So I don't get the wrong idea about that. So let's start talking about this big data end-to-end framework. And the first thing I want to do is just cover off on the Amazon services in this space. So a lot of you are very familiar with these, I know, but just so we're all on the same page, let me just go round the clock and quickly just cover off what Amazon's got in this space, and then we'll see how it all fits together. So in the middle, we've got Amazon S3, simple storage service, great place to store objects and files, etc. Very scalable, very durable. At 6 o'clock, we've got Amazon Glacier, same as S3, but a lot colder. That's basically a long-term storage archive. So it's much cheaper to store data in Glacier than it is in S3, but it takes longer to retrieve it. Going clockwise, we've got Amazon RDS. That's our relational database service. So that's a managed database service. So what that means is we'll manage the infrastructure underneath for you. We'll patch it, we'll back it up, we'll install the software, and then you just get to use that database as you would normally. That comes in 4 flavors: MySQL, Postgres, Oracle, and SQL Server. And it is your traditional relational database as you know it and love it today. Up at 10 o'clock, we've got Amazon Redshift, also a relational database, a managed relational database. But this is targeted at analytical workloads, as opposed to more of a transactional workload that you would get with RDS. And we'll look at that in a bit more detail as we go through. At 12 o'clock, we've got Amazon Kinesis, very exciting new service that's designed for real-time analytics, so the ability to ingest data in real time and then analyze it, do something with it. We'll have a bit of a look at that. Amazon DynamoDB is our NoSQL database. Now, we're not going to talk a lot about NoSQL today, not because it's not awesome, but just because it doesn't quite fit into the processing framework that we're going to be talking about. We don't really have time to cover it off. But NoSQL for certain use cases is phenomenal. At 3 o'clock, we've got Amazon Machine Learning. This is a brand new service, hot off the press, which, again, we won't cover in any great detail, but is a great way to get into the machine learning space. And then we've got Amazon EMR. So that's our Elastic MapReduce service. And again, it's a managed service that gives you a Hadoop cluster. So we'll spin up the EC2 machines, we'll install Hadoop, we'll make sure that all the nodes are talking to each other, make sure it's all up to date, and then we tie a nice big red bow around it, and we hand it to you, and you can start using it. As you'll see, the theme as we go around here is all about managed services. It's all about removing the undifferentiated heavy lifting from you guys so that you can start to use and analyze and do the fun stuff much more quickly. Now, so this is the Amazon offering in the big data space. But even just with our own services, there's overlap with the different services and hence questions about what I should use and when I should use it. So for example, a lot of questions around, okay, RDS is a relational database, Redshift is a relational database, when should I use which one? That's a valid question which we'll cover off later on. Also, Redshift and EMR, they're both designed to deal with large data sets and process those data sets. When do I use EMR? When do I use Redshift? So you can see, even in this set of services, there's questions around which service to use. Now, you layer on top of our services our partner services, third-party software, open source projects. This is obviously just a very small slice. You can start to see it becomes very confusing, and it's not immediately obvious what's the best service and what's the best technologies to use for my particular use case. So that's what I want to try and do, is put some structure around some of these and I'll give you a framework to use. Now, one of the other things I want to cover off on this, and I saw a quote the other day that perfectly summed up what I was actually trying to say here, and it was basically this quote. So this is true across all of IT, right? We always have these religious debates about which is better. And you kind of expect that. But normally you expect it in a certain category. So my relational database is better than your relational database, that kind of thing. But in the big data space, we seem to have taken it to a whole new level now, where whole categories are trying to deliver a knockout blow to other categories. So the Hadoop camp is saying Hadoop's the future, relational databases are dead. The NoSQL guys are saying, hey, NoSQL's the future, relational databases are dead. And the relational database guys are saying, why are you picking on us? You know, we've been good friends to you for very many years. Why are you pronouncing us dead? But the key point here is that it really doesn't matter. Certainly our view on this is that it's not a one-size-fits-all type of approach. Every bit of software, every technology, every service has got its good points and its bad points. You use what is best for your use case. And as we see as we go through, sometimes that might be an Amazon service, sometimes it might not be. For us, it's all about what's best for your particular use case. So we're going to, as the framework, we're going to use this long tube. This is a magic tube where you put data in one end and your answers magically pop out the other end. But basically the process is this. We're going to look at how you ingest data into the cloud, where do you store it, how do you process it, and then what do you use to analyse it. So let's have a look at ingest first. Now the way I like to split up ingest is depending on the different types of data that you have. This is going to depend how you get it in there. So databases is probably the most common type of data. Everyone's got a database in their environment. And the typical use case here is I have a database. It's probably a transaction processing database supporting some kind of application. I want to do some reporting, some analysis on it, but it's too slow. I'm not getting results fast enough. I want to look at more history. I want to look at more detail. And the database is simply just running out of puff. It's just not giving me what I need. So I want to move it to something that's a bit more performant. So we'll look at where that goes. And the types of data we're talking about, sales data, customer data, you know, the types of stuff, ERP, CRM, all sorts of stuff. Then we've got what I'm calling file data. Now, file data is typically event data, so it's transactions, it's events that have happened on some kind of processing engine, but they come at you in chunks, big chunks. It might be a daily chunk, it might be an hourly chunk, full of 1,000 or 1,000,000 different events. And you can see some of the processing frameworks there. So Log4j is a logging framework, Flume and FluentD are log aggregation services that can take logs off different machines and push them into one central place. So file data is another type of data you need to deal with. And it's things like web logs, server logs, that kind of machine-to-machine type stuff. And then we've got streaming data. So streaming data, similar to file data, can be events. So it's often an event or a transaction that's happened. The difference is that instead of coming at you in a big chunk, it's fired at you as it happens. So you're getting thousands or millions of tiny little events happening all the time, that kind of real-time streaming scenario. So it might be clickstream data, it might be sensor data, so you might have a network of sensors that are sending information about readings that they're experiencing. You want to capture those and do something with them. And we'll spend a bit of time talking about that because it's a really interesting area at the moment. So there are three types of ingest. So let's look at storage. So profoundly, database data typically goes into another database. Now, it doesn't have to. It can go into other places. But the common use case that we see is it goes into another database. And the reasons for this are pretty simple. Firstly, the data is highly structured already. So it's in a database. It's got that structure. So you may as well keep it in a structured format. The data might have relations between tables. That's all been set up. So you may as well reuse that. Plus, you've obviously got SQL skills and database skills in your organisation because you've got that original database. So you want to also utilise those skills when you move to your analytical database as well. Now, there's a couple of different database options. I'm going to look at Amazon Redshift and Amazon RDS. But when I do that, I want you to think about not just these two services, but the fact they represent their tribe, if you like. So Amazon RDS representing the tribe of traditional relational databases, MySQL, Postgres, SQL Server, etc. And Amazon Redshift representing the newer breed of analytical MPP, massively parallel databases. And we'll look at that as we go through. Now, getting data out of a database can be a little bit tricky if you want to do it in an ongoing change data capture kind of way, if you want to capture the changes. So often we'll work with partners in that area. So there's a couple of really good ETL tools that we work with. So ETL standing for extract, transform, and load. I've just put two up here. There's quite a long list that support Amazon really well. This is just two of the ones that we work with quite a lot. And they will help you to get data out of those databases and push them into the cloud. So let's just have a little chat about Swiss Army knives. The traditional relational database, part of the reason that it's kind of been knocked so much recently is that over the years, it's been asked to do a lot. It's become the Swiss Army knife of processing. Have a processing problem, put it in the database. And the problem is that over the years, we've developed fairly specific types of applications. So we've been asking the database to support web transactions, so potentially thousands or tens of thousands of transactions a second. We've asked it to do search. We've asked it to do complex transactions, hot reads, logs, analytics. We've said do it all. That's why it's been struggling. So what's happened in the last few years is we said, let's break out those specific tasks into best-of-breed specialised engines. So that's why you've seen the rise of NoSQL databases, because people were frustrated with the ability for a relational database to support web-scale transactions. That was kind of the reason for being for the NoSQL databases. And so they support that use case really well. Search obviously goes into a dedicated search engine. There's dedicated caches for those hot reads. Logs can go into an object store. The data warehouse is where you do your analytics. And so I believe that the traditional relational database is actually stronger than ever because it's now being allowed to focus on what it's good at, which is complex queries and transactions. Everybody uses a relational database in their environment to do transactional workloads, which is what they're good at. And so I think you'll see the relational databases go from strength to strength because they've offloaded a lot of this other processing. Now, Amazon does have services in each of those categories. I'm not going to go through those. I'm just going to focus on those bottom two on the right there, Amazon RDS and Redshift. And we're going to put them head to head. We're going to put them in the ring together to fight it out. And we're going to look at it along these lines. Now, remember, these are representing their kind. So RDS, traditional relational, Amazon Redshift, MPP database. So firstly, this is important. The types of databases that they are is the same. So they both support ANSI standard SQL, and they're both fully relational. Now that's important because some people think that when you move to an MPP database, you don't have joins, you don't have relations, it's not really SQL. That's not the case. Full ANSI standard SQL, full relations. So you could pick up your data model with all its joins and relations and put that into an MPP database and then query it as you would normally and it'd be very happy. But here's where they differ. In the architecture. So a traditional relational database is based on an SMP architecture. Now SMP is a bit of a 90s acronym that you don't hear much anymore that stands for symmetric multiprocessing. And really what it means is that those machines are really good at sharing resources in a single machine or a small cluster of machines. And that's why they get such great performance for transactional workloads. So I like to think of the SMP databases as a bit like my 7-year-old daughter. She loves to share. Great at sharing with a family, sharing with her friends. The MPP databases are my 4-year-old. Hates to share. Doesn't want to share anything. Now that's normally bad. I'm always telling her to share. But in the database world, if you're trying to scale, you want your nodes to be selfish. You want selfish nodes that keep to themselves and don't share resources because that's how you scale. So when you add a node to an MPP database, it's got its own disk, it's got its own memory, it's got its own CPU. It doesn't need anything from anyone else, so there's no contention for resource. So that's why when you look at scaling, the traditional relational databases scale vertically, so if you want to make it go faster, you've got to get a bigger box. But the MPP databases, you scale them horizontally. You add more nodes, and you'll get returns in terms of performance. So if you double the number of nodes, you should halve the response time for a query. Should be nice and linear. And that's fantastic. Storage is also interesting. So the relational databases, the traditional relational databases store by row, which is fantastic for transactional workloads because you're reading a row at a time or you're writing a row at a time. Not so good for analytics because you only want to read maybe a couple of columns, but you want to read a lot of rows. If the data's stored in rows, you've got to read a lot of redundant data. And I/O is the enemy of good performance when you're doing analytics. So if you look at Redshift is a columnar database, stores the data in columns, and that basically means that when you go to run a query where you're looking at a few columns but lots of rows, the system can just suck those off the disk really quickly, and you're not reading redundant data. Which leads us to the workload. Traditional relational databases, fantastic for transactional workloads. MPP databases like Redshift, fantastic for analytical workloads. Now, the question then becomes, at what point does it make sense to move to an MPP database? How much data do you need to have to make it worthwhile? Now, there's no hard and fast rule here, but my rule of thumb generally tends to be between 50 and 100 gig is kind of where it makes sense to move across. I've got some customers who've got 10 gigabytes, and they love the performance that they get from Redshift. Depends on the type of processing you're doing. But probably around that 50 to 100 gig mark is where you'd probably start to look. Quick customer example, Financial Times in the UK, they moved from an on-premise traditional relational database to Redshift. They talked about some of their queries running 98% faster. I'm not actually quite sure how you calculate that in terms of time. My maths isn't as good enough for that, but basically it's pretty quick. So let's look at where the file data goes. Now, you've got a couple of options here. Your file data can go into a specific application, or it can go into more generic storage. So the specific applications I'm thinking about are things like Splunk and Sumo Logic, which you might be familiar with. These are dedicated software packages that give you out-of-the-box functionality for reading machine-to-machine data, making sense of it, analysing it, looking for security issues, that kind of thing. Great tools. If you want a slightly more generic solution, you might want to put it into some kind of storage system. The two we're going to look at are HDFS, which is Hadoop's file system, and S3, which is Amazon's object store. So looking at HDFS first, HDFS is the file system embedded in a Hadoop cluster. So Hadoop sits on top of HDFS and uses that to distribute data in the cluster. Now, the key point about HDFS is it's got to have running compute underneath it. You've got to have running machines for HDFS to sit across, because it uses the storage on those machines. Now, in the Amazon world, you can either run this cluster yourself, so you can, those compute machines can be EC2 machines, you can spin them up, you can install Hadoop, HDFS will come with that, and you're ready to go. Or you can use Amazon Elastic MapReduce. And so what Elastic MapReduce will do is it will do the management of those three rectangles for you. It will spin up the EC2 machines, it will still install Hadoop, it will make sure they're all talking to each other, and basically you're ready to go. Either way, you've got a running Hadoop cluster that then allows you to take advantage of the massive Hadoop ecosystem of tools out there. So this is just 6 of them, but there's hundreds. They all plug into Hadoop. And so if you've got your data sitting in HDFS, you can use those tools to then start to do analysis, transformations, you name it. Now contrast that with S3. So S3, there's no compute underneath, it's just storage. And the idea is that if you sit in S3, you've then got the ability to move into different other processing options. So yes, you can push it into EMR, you can push it into Redshift, machine learning, NoSQL, or of course, any other non-Amazon application as well. So S3 potentially gives you a bit more flexibility in where that data goes. And of course, you can archive it off to Glacier as well if you wish. So let's do another head-to-head. So HDFS and S3. In terms of durability, HDFS has got a configurable option. So it'll write data by default 3 times to different places within the cluster, every object. With S3, obviously, that is built in. So we'll automatically write every object to 3 different physical locations for you. In terms of the cost, HDFS tends to be higher because you've got to have running compute underneath. Whereas with S3, there's no running compute, it's just storage, so it tends to be a little bit cheaper. In terms of scaling it, if you want more space in HDFS, you've got to add more nodes to your cluster. With S3, obviously, it's just automatic. You just load up more data. Now, it might seem that I'm deliberately skewing this towards S3, but have a look at this last point, which is that HDFS tends to be a little bit faster. And the reason for that is because if you've loaded your data into HDFS, the cluster's already running, because it has to be, and obviously your data's already local, it's already there. Whereas with S3, you've got to move it to wherever you're going. So again, as I said earlier, it depends on your use case. If your use case is that you get maybe a chunk of file twice a day, then maybe you don't want a running cluster all the time. You don't want to pay for a constantly running cluster. So you put that file in S3, you spin up a Hadoop cluster, you suck the data in, you do your processing, you shut the cluster down. Stop paying for it. Or your use case might be you're getting chunks of data every 5 minutes. Then it makes sense to have a running cluster. You may as well have that in HDFS. So again, depends on your use case. And there's hybrid options, of course, as well, so you can use both. A good example of that was FINRA, the Financial Industry Regulatory Authority in the US. These guys are tasked with looking at 30 billion trades a day that happen on the US stock exchanges and looking for fraud. Obviously, they want to do that in a fairly timely fashion, as you would. What they do is they suck that in to S3, then they spin up big Hadoop clusters and they push that processing through those clusters. When they talk about the benefits that they got, they talk about agility, they talk about performance, and they talk about cost. But the other interesting thing they talk about is they talk about avoiding vendor lock-in, which I thought was quite interesting. And the comment that he made was that because the big data world is moving so quickly and technologies are coming and going and changing, he didn't want to get locked into a particular proprietary technology. He wanted to stay agnostic, and he felt that doing that on Amazon was the best way to do that. Let's move to streaming data. So streaming data typically goes into some kind of stream processor. And a couple of options we're going to look at. We're going to look at Amazon Kinesis, and we're going to look at Apache Kafka. Now, the first question is, why do you need stream storage at all? Why don't you just spin up some orange boxes, which represent EC2 machines, and then just fire all of the data at them, and then just collate it that way? So let's assume that the data we're trying to collect is from sensors. So this is a real-world example from one of our customers who deploys sensors throughout buildings, and they're looking for things like temperature, humidity, vibration, all of that kind of stuff. And those sensors send information every 10 seconds. Now, you could do this. You could just spin up a lot of EC2 machines and ingest the data that way. But what you lose is you lose the ability to analyze data from a single device in a meaningful way. So what I mean by that is if we color code these arrows, so if you think of the color of an arrow representing a single device, so with the red arrows, say that's coming from a single device. So some of their messages are going to the top node, some of their messages are going to the bottom node. So we can do things like, we can have alerts that say, if the temperature hits a certain, or is out of band, then send an alert, do something about it. But we want to do something more meaningful. We want to know, is this temperature trending up? Is it trending down? How fast is it trending? Well, you can't do that if you don't have access to all the information from that device. So what you need to do is you need to group those messages in some way. So this is why we had the stream processing engine, which basically captures the messages, then groups them in a way that you specify before it then gets processed. So now you can see all the red arrows have been grouped together. So they all get processed by the same worker. So that worker can then look at, is this trending up, down, how fast, whatever, because it's got access to all of the information from that device. Okay, and that's key. And that's obviously where the Amazon Kinesis or Kafka sit in there. So looking at this in a bit more detail, we'll look at Kinesis, but Kafka is very similar. Kinesis sits across 3 availability zones. So an availability zone you can think of as a separate physical data center. So every message we receive, we'll write it 3 times. You create a stream that gives you an endpoint that you can then tell your devices to write to. They push all their messages into Kinesis. And then at the back end, you've then got your applications that are consuming this data. And so the typical pattern here is that you have multiple applications that are doing different things with the same data. So a classic one is, okay, I want a log of everything that's happened. I just want an audit log, all the raw data. I need to keep it. I need to know what happened at any time. So that will probably just be written to S3. But I also want to pull out some metrics. So I want to see a real-time dashboard. I want to know, are these buildings all right? What's the temperature trending? So I might push some metrics. I'll pull some metrics out of the data stream and push that into a NoSQL database like Dynamo. Put a dashboard over the top, and off we go. But then I might want to do deeper analytics. I might want to do year on year or season on season. So maybe I want to push some data into Redshift so I can look at the historical information as well as the new information. Or I might even want to do something even more interesting. I might want to push it into something like Apache Storm, which is a complex event processing engine, a distributed one. Now, the key thing here is that you can do all of that because each of these applications do not interfere with one another. They all reach into the stream at potentially different times, but they've got their own checkpoints, so they're not going to interfere. So that's one of the great things about using a stream processing engine is that ability to use different applications. Let's put Kinesis and Kafka head to head. In terms of latency, it's supposed to be real-time streaming, so the latency had better be low. We're talking about potentially opening this up to the internet, so the scaling had better be high. They both respect the ordering that messages come in. That can be important. But this is where they differ. Kinesis will hold a message for 24 hours. Kafka, that's configurable. Customers tell us 24 hours for most use cases is okay, but obviously if your application sits outside of that, then maybe you want to look at Kafka. Again, the size of the payload, the size of the message. 50K in Kinesis currently, configurable in Kafka. Again, most customers say 50K is enough, sometimes it's not. And again, not to harp on about the managed service thing too much, but Kinesis is a fully managed service. Kafka, you've got to do that yourself. A fantastic use case is one of our gaming customers, Supercell, and they use Kinesis to capture in-game analytics, in-game messages. Where are their users up to? Is somebody having an issue playing this particular level? And they capture that information, and it gives them a much richer and real-time view on what's going on in their gaming world. And they talk about the world of gaming never sleeps. I've got some friends who are gamers who never sleep. And they talk about owing every player a great experience, and they basically use AWS to make that happen. So we've looked at ingest and store. Let's have a look at process. Now, process I'm going to look at from three angles. One is interactive. So my definition of interactive is that you've got a human who's actually sitting there waiting for something to finish. So it had better finish quickly because you want it to be interactive. Batch. So my definition of batch is you hope there's not a human sitting there waiting for it to finish because it's going to take a long time. And then obviously you've got to do something with the streaming data as well. So Redshift sits squarely into the interactive camp. Designed to be interactive, designed to have people using it, designed to allow you to ask questions at the speed of thought, get an answer back, ask another question, kind of drill down through the data. But there are other options as well. So there's open source options like Presto, which came out of Facebook, Impala, and they sit on top of Hadoop or EMR. So looking at those three head-to-head, again, latency is low, so you want quick response. Durability is high. They all scale up to pretty high volumes. The storage of Redshift is native, so the storage is direct attached. With Impala and Presto, they're either talking to HDFS, or in Presto's case, they can also talk to S3. So that hybrid case I talked about, where you might have some data in S3 and some in HDFS, Presto's great for that. BI tools, typically Redshift's got a few more just because it's been around longer. And again, Redshift is a fully managed service. Impala and Presto, I've said they're semi-managed because if you're using EMR, then the Hadoop bit's managed. The top bit's not, the Presto bit's not. If you're managing the whole Hadoop cluster, then obviously it's completely managed by you guys. Moving on to batch, there's lots of different options here. I just wanted to cover off on three. So Spark is kind of the new kid on the block in terms of processing. So often you hear Hadoop and MapReduce talked about in the same sentence. MapReduce has been the processing engine for Hadoop for a long time. A lot of people don't like it because they think it's too slow, too batch-oriented. They've moved more towards Spark, which gives you the option to do batch, but also potentially interactive as well. So you'll hear a lot more about Spark in the coming months and years. Hive was kind of the original SQL on Hadoop interface, so people wanted more of a SQL interface into Hadoop. Hive was the first one. Again, gets pinged for being very slow, but it's a bit of a workhorse. It's pretty ubiquitous. My favourite is Pig. Pig eats everything. That's why it's called Pig. It's a transformational engine, so basically you feed it messy data, semi-structured, unstructured, and then you can use it to basically put some structure around it. Again, the fun stuff with Hadoop is the names of things. Like Pig's funny, but when you put Pig on top of Spark, you get Spork, which is even funnier than Pig. Sorry, it's a bit late in the day to be showing you graphs, but just a quick one. Now, I'm not showing you this because Redshift does particularly well on this. I'm showing it to you for a couple of reasons. One is it shows you the kind of the Hive batch versus some of the more interactive stuff. So lower numbers are better here. So this is query response time. So if you look at Hive, big long bars, takes a long time to do anything, but you look at Redshift, Impala, nice short bars, interactive speed, you can ask a query, get a response back. The other thing worth pointing out on this is this was done about a year ago by Amp Labs, and it's already out of date. So you'll see Shark up there. So Shark is Hive on Spark. Unfortunately, quite a good name, but has now been deprecated in favour of something else. So even in the world of big data, things move fast. So Shark's gone. And all of those numbers, if they ran that benchmark today, all of the numbers of those technologies would be a lot lower. There's been advances across the board in all of those different areas. So as I said, things change, but things get faster and better all the time. Moving on, let's do streaming. So we've had a look at this already. So basically, Spark has got its own streaming engine. Kinesis consumers, which we've looked at, will consume the data coming out of Kinesis and do something with it. Apache Storm is another complex event processing engine. I wouldn't see Apache Storm and Kinesis as competitive. Normally, they're used together. So there's actually a connector for Kinesis that will go into Storm. So that's kind of the process side. Now, on top of that, you then want to start to analyze the data. And I've broken this into three main areas. The first is your traditional business intelligence types of tools. So things like Tableau, Jaspersoft, Business Objects, MicroStrategy, Cognos, you know the ones. Fantastic for that kind of business intelligence type of reports and analysis. But then you might want to get into more statistical type of analysis. So things like SAS, R's becoming very popular. You can plug those in as well. And then you've got machine learning. So as I said, Amazon Machine Learning has just come out, but there's other fantastic open source options as well, like Mahot, for example, which again sits on Hadoop. So that's the framework that I wanted to build up for you. Now, that's just some of the common ones that we see. Obviously, there's plenty of technologies we haven't covered here, not because they're not fantastic and applicable in a lot of use cases, but simply because we just wanted to, cover off on just the main ones that we see. So let me layer some use cases on top of this. And let's talk about fear of missing out. So one of the things I hear sometimes is, wow, look at all those fantastic technologies. There's all these amazing things out there. If we're not using them, we're missing out. And people have this fear that they're somehow missing out on all this great stuff. But the thing is, some of these technologies will give you what you need without necessarily having to get into some of the more complex stuff. So a good example of this is SQL Analytics. So you look at SQL Analytics where you want to be able to get deeper into your data, look at more detailed data, look at more history, have it come back faster. You could simply just take your database data, put it into Redshift, lay a Tableau off the top of that, and you're done. Redshift gives you the scalability and the speed to run those queries and get deep into the data, and Tableau gives you that rich visual environment in order to drill down into it. You don't necessarily need to get into Hadoop and Spark and Spork and Pig. You can stick with a database technology that you already know how to drive. So my point there is, don't necessarily feel that if you're not using Hadoop, you're missing out. It could be that just that your use case, you're getting what you need out of other technologies. Another common use case is clickstream analysis. A lot of people do this in batch. So they'll use something like Log4j, which will do their logging for them, push that event data. Maybe they push that straight into HDFS. That might be running on EMR or Hadoop. They spin up some of the tooling, and then they run some analysis tools over the top of that. You can also do that in real time. So you might have an event producer that's actually firing every time someone makes a click. That might go into, maybe that goes into Kinesis. The Kinesis consumers will then write that into S3 for an audit log. They'll also write it into Amazon Redshift for people to analyze. That might be with Tableau, for example. And then they might push something into machine learning as well. The last one to look at is the data lake. Now, the data lake is a term that a lot of people don't like because it's been a little bit overused, which I agree with. But the key message behind the data lake is actually quite interesting, and a lot of it's to do with self-service analysis. And it's basically put the data in a place where your users can then self-serve, where they can spin up the technology that they want to use and consume the data. So for example, you might have database data, event data, streaming data. You put that in S3, Kafka takes the streaming stuff, and then people can spin up the tools that they want. So if they're familiar with Hadoop, they might spin up a Hadoop cluster, use that to analyze the data. If they're more database people, they might spin up Redshift. And then they can use the tools that they want to do that. And the key here is that you're not necessarily paying for all this processing 24/7. People spin stuff up, do the processing they need, and then they shut that processing engine down again. So that's becoming an interesting conversation that I'm having with a lot of customers, is that kind of data lake enterprise hub type of approach. Right, now, what I wanted to do now is just jump into a little bit of a demo just to finish off and do that with machine learning. So hopefully the demo gods will smile on us. So machine learning, for those of you who are not familiar with it, is basically, the tenet is that machines are better and more efficient at spotting patterns in data than humans are. Typically, not always, but for a lot of use cases, they're much better at it. And so what you do with machine learning is you first of all have to train the machine into what you're actually looking for. So what you typically do is you feed it a training set of data which has got all the information in it plus the answers that you're looking for, and it then will learn what patterns in the original data led to the outcome. So an example might be that you're looking for fraudulent credit card transactions. So when you're training it, you feed it a set of data that's got the credit card transaction, so the timestamp, the user, the amount, the merchant, the location, all that stuff, plus you tell it the answer. So you say, this was a fraudulent transaction, or no, it wasn't. And the machine will then look for patterns in the data to work out what actually leads to that outcome, what leads to it being a fraudulent transaction or not. So what we do with Amazon machine learning is that when you fire it up, which I'll show you, you feed it a training set, and what it then does with that training set is uses 70% of the data to create the model, and then holds back 30% to then test itself. So once it's created the model with the 70%, it then uses that remaining 30%, makes predictions about what it thinks the answer should be, and then checks against the answers, because remember that 30% still got the answer in there. And so it does those checks, and then gives you an evaluation. So basically says, this is how I went on that 30%. Do you think this is okay or not? And if you're happy with it, then you can then put that model into production and then start feeding it raw data that doesn't have the answers in it. And it will then start to make those predictions for you. So let's just use a simple case. So what we're going to use is a data set that came out of Kaggle. A lot of you might be familiar with Kaggle. So it's basically a site where they'll set up a competition, a data science-y type of competition, and they'll say, here's the data set, this is the outcome that we want, go and produce an algorithm that leads to an outcome. And so the data set that they had was basically a lot of cities now around the world are providing bikes to their citizens to say, if you need to ride home, here's a bike that we'll lend you and you can ride home and then leave it somewhere. And the trick there is obviously knowing how many bikes you need on a given day based on the weather, the time of day, the season, etc., etc. So the data set has actually got by hour the number of bikes that were used, the weather, the season, all that information. And so what we want to do is we want to feed that into the machine learning algorithm for it to then learn basically how and predict how many bikes are going to be needed on a given day. Now, as we go through, you'll notice that I've created a few objects already, and this basically just allows us to kind of skip ahead so we're not sitting around waiting for things to happen. So it's going to be a bit like a cooking show where we're going to pull one out of the oven that we've prepared earlier, just so that you're not sitting there watching me wait for stuff to happen. So the first thing we're going to do is create a data source. Now what this will do, this will allow machine learning to pull data either out of S3 or Redshift, and this is going to be our training set of data. So it's looking at my buckets, and we're going to use this data set here, which is my training set. Okay, I'm just going to call this demo train. Okay, we'll verify that. What it's going to do now is it pulls out of the, so basically that's just a CSV, right? It's just a comma delimited file. It pulls the schema out for me to have a look at to make sure I'm happy with it. And the first question it asks me is, does the first line of the CSV actually have the header in it? Now in this case it does, which makes things a little bit easier because we know what we're looking at. So I'll choose yes there. So you can see now on the left-hand side I've got all the names of the columns. And it's made a guess as to what kind of data type each of these rows is. And there's basically 4 options. It's either a numeric, a binary, so 1 or 2 values, categorical, so multi-value, or it's numeric, or it's text. And this just helps it to, when it's doing its algorithms. So most of these I'm happy with. The one I'm going to change is weather. So it thinks weather's a numeric because basically it's got a number between 1 and 4, but those numbers actually represent how the weather was on that day. So, 1 is sunny, 2 is cloudy, 3 is windy, 4 is torrential rain. So I'm actually going to make that categorical, which will actually make the algorithm a bit smarter. Now the next thing it's asking for here is, what's the target? So the target is the actual column that you want it to predict. What are you actually asking it to try and work out? So in our case, it's the numbers of bikes that were actually used on that day. That's what we're trying to determine, how many bikes were used in the training set. And then later, obviously, when we feed it raw data, we want to know how many bikes do you think, Mr. Machine Learning Algorithm, we're going to need for a given day. So that's our target. So it knows what it's aiming at. Okay, I'll just take the defaults there. Okay, so that's going to go and do that. So where we're up to in our model here is that we've basically pointed the machine learning service at the training data set. So that's currently pulling that in, doing some analysis on it. Now, instead of waiting around for that, I'm going to jump to a data source that I prepared earlier. So this is basically one that I went through the same process that I just went through with that one. And what we're going to do is then we're going to ask it to create a model for us. Okay, so we'll give that a name. Now, I'm taking the defaults as we go through here. There's several stages where you can tweak the algorithm as you go along, but I'll leave that for you for some homework to do, to go and read up on the documentation and work out how that all works. So what it's doing now is it's now building that model based on that data set. So if we go back to our pipeline, it's now doing this 70%, 30% split. So it's now taken 70%, it's running that through the model, kind of creating the model. It's learning about the data set. And then after that, it's going to push the 30% through, and then it's going to push out an evaluation. So again, let's jump ahead. So here's an evaluation of one that we did earlier. And you can see in green here, it's basically giving us a summary as to how well it went when it tested itself on that 30%. And it uses something called RMSE, which is basically the root mean square error. And I've got no idea what that means. But what I do know is that lower numbers are better. So you can see that our value was 42, the baseline is 61. So it's basically saying, look, we think the model's pretty accurate. We can actually delve into that a little bit further if we go into here. Now, what this graph is showing us is that dotted line in the middle, that dashed line in the middle, is the actual number of bikes that were used for each row. And the bars on either side are the prediction that the algorithm made. So the further away it gets from the dashed line, the worse the prediction was. Now, the key thing you're looking for here is that the mistakes that it made kind of fall evenly on either side of the dashed line. So you know it's going to make mistakes, right, because it's just a model. But you want it to be balanced. So the ones to the right of the dashed line is where it overestimated how many bikes were going to be on that day, and to the left it underestimated how many. But if the graph looks like that, then that's kind of okay, because sometimes it's over, sometimes it's under. If it's all to one side of the dashed line, then you've got a problem, because if all of those bars are to the left, it's always underestimating how many bikes are supposed to be there. Okay, and you don't want that. So there's something flawed in the model or in the training set that you gave it. But that I'm pretty happy with. So what that means is then we've got this model that we're happy with, and then we can use that in a couple of ways. So one way is in batch. So we've got our model sitting there. We can then feed it a batch of data, so a CSV file with a whole bunch of entries in it, and it will then give us a batch prediction. So we give it a file, and it'll give us a file back. And that file that it gives us will basically contain all the predictions. So for every line, it'll give us the number of bikes it predicts for each given time period that we give it. The other option, and this is the interesting one, is to do it in real time. Same model, but this time you're feeding it real-time data. So that's that funny-looking thing on the left there, that's the Kinesis symbol. But it doesn't have to be Kinesis, it could be anything. Basically, you're firing a message at a time into the model and saying, and obviously for the credit card fraud transaction, you'd want to be doing it in real time. So you want to say, is this fraudulent? So you send in the transaction, all the information's in there. In 100 milliseconds, it'll make a decision and it'll give you a real-time prediction. Yes, this is fraudulent. No, it's not. And then you take that and obviously put that into a NoSQL database or something like that to basically then use that in your application. The applications of machine learning are extremely broad. You can use it in all sorts of different applications. We obviously just scratched the surface here. As I said, if it's of interest, have a look on the website. There's plenty of info, plenty of tutorials you can do, et cetera, et cetera. Thank you very much, guys, for staying around, being with us all day. We really appreciate it. I think we're doing the wrap-up next door. Thank you very much.